are doing lesson 9.1, and we are going to do part 1, all right? I said this already, but we're going to be looking at examples 1 and 2 in your notes, and then tonight in your flipped classroom, you will be doing lesson 9.1, part 2, which will be example number 3, all right? The entire lesson is about the properties of radicals. So before we get into anything, does anybody remember what a radical is? It has another name. Liz? A square root, okay? So the problems that you're going to see today are going to have radical or square roots in them. The essential question says, how can you multiply and divide square roots? And you can see I've given you this nice large example of what a square root is. Now before we go any further, let's review. If I'm looking at this problem, does anyone know how we read this problem? Anybody? The square root of 100, okay? So if we read this as the square root of 100, then what is the understood root that sits right here on this ledge?
2.
An understood 2, all right? And that is going to be key to things we're going to do today. You have to remember that if you don't see a number on the ledge, it is an understood 2, all right? So if you need to add that to your notes, please feel free. Now, the number that is under the radical, okay, also keep in mind there could be variables under the radical, but anything under the radical is called the radicand. So as you're reading these definitions right here and you see the word radicand, that's what we're talking about. We're talking about what's underneath the radical. So first of all, radical expression would be an expression that contains a radical. So when you look at a problem, if you see a square root sign in it, it's considered a radical expression. Now, these radical expressions have to be in their simplest form. If they are not in their simplest form, we cannot box them in. So here's how you know if they are in their simplest form. No radicand have perfect nth powers as factors other than 1. So here's what that means in layman's terms. There is not a perfect square under the radical. If there's a number under the radical that is a perfect square, then this problem is not in its simplest form. So highlight that. Okay, that's the first thing. No radicands have perfect nth powers. The second thing that cannot be true is it cannot contain fractions. If the radicand is a fraction, if the number under the radical is a fraction, it is not in its simplest form and we have to simplify it. The third thing, it cannot appear in the denominator of a fraction. So you cannot have a final answer that's a fraction that has a radical in the denominator. So all of these things, if any of these things are true, the problem is not in its simplest form. Now here's the next thing you need to know about putting radicals in their simplest form. We are not using a calculator today. In order to simplify a radical without a calculator, you have to know how to do upside down division. Upside down division is exactly what it sounds like. When you were in elementary school and you were trying to divide the number 24, you did 24 and then you put this nice little division bar over it. All right, upside down division is exactly what it sounds like. We're going to take that 24 and we're going to make that division symbol or bar upside down. Now there's keys to doing upside down division. The very first and most important one is you can only divide by prime numbers. I want you to highlight prime and let's review the first 6 or 7 prime numbers. Does anybody remember the very first prime number? 2. Very good. You skipped right over the 1, and that is perfect because 1 is neither prime nor composite. All right, what's the next prime number? Okay, let's talk about 4. Now hold on. I'm okay that we said 4 because let's think about it. Prime numbers have only factors of 1 and themselves. So 4, not only does 1 times 4 give me 4, but so does 2 times 2. So 4 is not prime. Okay? So we also skipped over the number 3. Is 3 a prime number?
Yes.
Yes, 3 is prime. All right, what would be the next prime number? 5, and then 7, and then 11. Good. 8 has 2 times 4, so it's not prime. 9 has 3 times 3, and 10 has 2 times 5. So we go from 7 all the way up to 11. And what's one more? 13. Now the reason I typically stop here is because when you do upside down division, you're thinking of small prime numbers. You don't typically have to get much higher than a 13. So make this list, even if you're like Ms. Johnson, I know all the prime numbers. Okay, that's great, but add this list into your notes. Now, The second thing you need to understand is you divide until you reach a prime number. So you're going to hear me say, is this a prime number? Is this a prime number? Because we have to keep dividing until we reach a prime number. The third thing we're going to do is we're going to circle pairs or sets. Now this is where the root matters. If we're looking at a square root problem, then we're looking for pairs. But what happens when our root goes up to a 3 or to a 4? Well, I'm looking for either sets of 3 or sets of 4 or sets of whatever my root might be. So we're circling pairs and we're making those pairs just one of that number. And we'll see this here in just a second. Fourth thing we're going to do, we're going to multiply all those numbers, all those pairs that we have found. We're going to multiply those numbers together, and that is what's being pulled out from underneath the radical. And then any leftovers get multiplied, and they go back under the radical. Now, you all said that you've learned this, so this should all be just a quick review. But let's go straight into example 1. It says simplify the expression. Now, the first question you should be asking yourself, is this a perfect square? Because if it's a perfect square, I'm not going to waste my time doing upside down division. So let's look at letter A, the square root of 24. Is 24 a perfect square? No, it's not. So off to the side, I'm never ever going to do my upside down division under the original problem. That's where I want my final answer to go. So over to the side, I left you room. We're going to do upside down division. Now what prime number goes into 24? 2. But is that the only prime number? What's another one?
3.
Does it matter if I start with 2 or 3? No. Half of you could start with 2 and the other half could start with 3. If you divide correctly, you're going to end up with all the same numbers at the end. So let's start with 2, because what is 24 divided by 2? 12. What's 12 divided by 2? Okay, and I gave you the answer. Is 6 a prime number? No. So what prime number goes into 6? 3. And 3 goes into 6 how many times? Twice. Now, is 2 a prime number?
Yes.
Then I am done dividing. Now, I don't know what you've learned in the past, but here's what I ask. Once you reach a prime number, stop putting the division bars. Because we are supposed to focus on all of the prime numbers we have. And my fear is if we have put the division bar there, we're going to forget that 2 is one of those numbers that we're supposed to be considering. So once you reach a prime number, I'm asking you to stop putting the division bars. Because now we can look for pairs. Do we have any pairs here?
2.
We have 2 pairs, or we have a pair of 2s?
A pair of 2s.
We have a pair of 2s right here. So we're going to circle the pairs. And then if you've ever been to a wedding and you've heard, this is the easiest way I can think to help you remember this. If you've ever been to a wedding and you heard the preacher say that these 2 people are becoming one, okay? These 2 number 2s are becoming one of that number, okay? So the pairs become one of that number. And I just draw a little line off the circle and I write down the number 2 one time. Now that is the number that is coming out from underneath the radical. So I'm going to put the number 2 and then I'm going to put my radical sign because my leftovers have to go back underneath. What numbers are left over? 2 and 3. And what am I supposed to do with the numbers that are left over? Multiply. Listen, if we're doing upside down division, what's the opposite of division? Multiplication. All right, so this is division and multiplication. So I multiply 3 and 2 back together, and that puts a what underneath the radical?
6.
The leftover of 6. So this is my final simplified answer. Let's look at letter B. You'll notice in front of this radical, what is in the problem?
A negative.
A negative sign. Does anybody know how to read that?
Negative 80 squared.
Okay.
Or,
That's a good try. All right, this technically is read the opposite of the square root of 80. You might say negative square root of 80. Either way, the negative is not going anywhere. It's simply coming down into our final answer. So go ahead and drop that down. Now, is 80 a perfect square? No. So we are going to go over to the side and we are going to do upside down division. Now, what prime number goes into 80? And what prime number goes in, or what other prime number goes into 80? 5. Okay? 5 goes into 80. Now, some of you are like, Ms. Johnson, I can't do this in my head, so I need to go off to the side and do work, okay? How about if you didn't have to go off to the side? What if you could do everything right here in the upside down division box? 5 goes into 8 how many times without going over? 1. But what is 1 times 5? 5, which means there's a remainder of 3. So I put the remainder beside the next number, And now I'm asking how many times 5 goes into 30. So I'm doing division just upside down. How many times does 5 go into 30? 6. So I can do 80 divided by 5 without a calculator. What prime number goes into 16? 2. Or 3, doesn't matter, but we'll do 2. 16 divided by 2 is 8. What prime number goes into 8? 8 divided by 2? 4. And what prime number goes into 4? 2. 2 times. Is 2 prime? Then I'm done. Now, half of you started with a 2 and half of you started with a 5. Do you all have 4 2s and 1 5?
Yes.
So it does not matter if you start with a 5 or start with a 2. If you divide correctly, you will end up with the same numbers. Now, pairs. Do we have any pairs now?
4 2s.
Okay, we got 2 pairs of 2. We got 2 there, and we got 2 here. So this pair becomes a 2. This pair becomes a 2. Now, this is the first time we've had 2 numbers coming out from under the radical. What am I supposed to do with both of those 2's? Multiply. And you know how we show all of our steps in our notes? So if we go back, we can see exactly what we did. That's what we're going to do here. I know we can all do 2 times 2 in our head, but we're going to write it down. So you got 2 times 2, and then let's go ahead with the radical. What is the leftover that needs to go underneath? 5. All right, and I'm going to move this over so we have room. Don't want to get it in there. So we got the 2 times the 2, and then we got the leftover of 5. Now, do your math. What's negative 2 times 2? Negative 4 times the square root of 5, and that is your final answer. All right, we decided that 75 is not a perfect square, so what prime number are you dividing 75 by?
5.
5. Now here we are again. 5 goes into 7 one time, but 1 times 5 is only 5. So there's a remainder of what? 2. 5 goes into 25 how many times? 5 times. What prime number goes into 15?
5.
How many times? 3. 3 is prime, so we stop dividing. Do we have any pairs?
Yeah.
What is our pair?
5.
We got a pair of 5s, and it becomes a 5. So that is what is outside the radical. Now, I'm going to put the radical and the leftover, but notice how I leave a little space, because there's a very high chance that some ends are going to come out when we learn how to simplify into the fifth. So leave yourself a little bit of space, but what leftover is going back underneath the radical? The 3. All right, awesome. Now, let me teach you how to do the variables. We already talked about the fact that when there is no number out here on this ledge, it is an understood what? Nope. This is a square root. So there is an understood 2. See, you've got to know this. If you don't know this, it'll throw everything off. Okay? This is an understood 2. So I want everybody on letter C, I want you to fill in the number 2 right there. And then I want you to take your highlighter and I want you to highlight the 2 and I want you to highlight the 5. We have to see how many times the root number will go into the exponent. So 2 goes into 5 how many times without going over? So guess how many n's are coming out? 2. So n to the second is coming out from underneath the radical. Now, are there any leftovers? That's the question. Well, what is 2 times 2? 4. And how many n's were under there to begin with? 5. So are there any left over? There is 1 n left over. So this is your final answer. 5 times n squared, or 5n squared. Now let's talk about this for a minute. You've got 5n squared and a radical with absolutely nothing between them. What operation do you think that is? Multiplication. So when I ask you to read these in a little bit, it's 5n squared times the square root of 3n. Now, for my visual learners, let me show you why 2 n's came out. If I were to put n to the fifth back underneath a radical, and I were to expand it, it would be n times n times n times n times n. Correct? I've got 5 n's. Now, it's all about pairs, right? So you've got a pair of n's here, and you've got a pair of n's here. Those pairs become what? One of that thing. One of that variable, one of that number. So this pair of n's becomes an n. This pair of n's becomes an n. And what are we supposed to do with those variables? We multiply them, right? Over here we had 2 2's come out and we multiplied them. So that's why n times n got us the n squared. And then how many n's are left over here? There was 1. So if you need to do variables this way, if you need to expand them out and find pairs, I'm all for it. I'm okay with it. But really, the shortcut is you take the root number and see how many times it goes into the exponent. Now, same directions. We've got D, E, and F. What do you notice right off the bat about D, E, and F? What is underneath the radical on all three of these problems? Fractions. Is that not one of the things we said cannot be happening if our problem is going to be in simplest form? So here's what we're going to do. First of all, I want you to look at letter D. What's out in front of the radical once again?
Negative.
A negative. So let's just bring it down. It's going to be in our answer. Now here's what we're going to do with fractions. When we see fractions underneath the radical, we're actually going to split the numerator and the denominator. And here's what I mean. I'm going to put a radical over just the numerator, put my fraction bar, and put a radical over just the denominator. So I'm going to say the square root of 17 divided by the square root of 100. Now let's talk about the 17. Is it a perfect square? No. Could we do upside down division on it? But is it going to matter? What is 17? A prime number. So we know it's not going to simplify any further. So we're keeping the negative and we're keeping the square root of 17 in our numerator. Now, you've got the square root of 100 in the denominator. What's the square root of 100? 10. This one's a perfect square, so there's no reason for me to do upside down division. I'm finished. Look at letter E. What's the first thing we need to do? Okay, split up the numerator and the denominator. So the square root of 36 divided by the square root of z squared. Is 36 a perfect square?
Yes.
What's the square root of 36? 6. And what about z squared? Is that a perfect square? What's the square root of z squared? Z. And once again, we're finished. But do you see how much easier it is to visualize when we split up the numerator and the denominator? What's the first thing we do with the fraction underneath the radical? Separate it. So we've got the square root of 4x squared divided by the square root of 64. Is 4 a perfect square?
Yes.
Yes. So what does it become?
2.
Square root of 4 is 2. And what about x squared? The square root of x squared is x. Divided by is 64 a perfect square?
Yes.
What is the square root of 64?
8.
8. Now, before you box this in, this is a fraction. What do we always have to do to fractions?
Simplify.
Simplify. Will this 2/8 simplify?
Yes.
To what?
1/4.
1/4. And of course, we got to keep the x in the numerator. So you can put the 1 in front of the x or you can leave it off. It doesn't matter to me. But 2/8 absolutely reduces to 1/4. All right, we're going to keep on simplifying the expression. But look at the note that I've added above G, H, and I. It says to use upside down division, which we've been doing. That's not going to change. But circle sets of 3 instead of pairs. So I want you to fill in any blanks I left. I want you to highlight. And I want somebody to tell me, why are we no longer circling pairs, but instead circling sets of 3? Liz.
It's being rooted to the power of 3.
The root is 3. So once you have filled in the blanks and highlighted that statement, I then want you to go to G, H, and I want you to highlight the root. This is why we're finding sets of 3 this time. If that was a 4th root, we would be finding sets of 4. Okay? So I need you to understand that. But what do you notice right off the bat about 54? Now, we can't ask, is it a perfect square, because these are not square. We can ask, is it a perfect cubed root? Is there a number times itself 3 times that will give us 54? Okay, you're like, I don't really know. That's okay. Upside down division works every time. And if it were a cube, a perfect cube, that will come out in upside down division. So let's go ahead over to the side and let's do upside down division on 54. What prime number goes into 54? 2. Now, 2 goes into 5 twice. With 1 left over, 2 goes into 14 7 times. What prime number goes into 27? 3. How many times? What prime number goes into 9?
3.
How many times?
3.
3. Now, sets of 3, because the root is 3. Do we have any sets of 3?
Yes.
Yeah, we have 3 3s. So once again, we circle the set, and once again, the set becomes just one of that number. So 3 comes out from underneath the radical. Now be careful, because when you put your radical for the leftovers, you've got to include the root out on the ledge. But what is the leftover that goes back underneath? 2. So nothing has really changed except we found sets of 3. And when we put the radical in our final answer, we have to put the root on the ledge. Now look at letter H. What do you notice right off the bat about letter H? It's a fraction. So what are we going to do first? Split them up. So we got the cubed root of A divided by the cubed root of negative 27. Now, we've learned this. So let me ask. When there's a negative number under the radical, are we allowed to continue working the problem? Okay? The answer is yes. For this problem. But why are we able to work this problem? Typically, I would agree. If there's a negative under the radical, we're done. We say no solution and we move on to the next problem. Except when the root is what kind of a number? Odd. Do you remember learning this? We've learned this already. When the root is odd, we can work with the negative number under the radical. So we're going to continue this problem. Now, can we do anything with the cubed root of A? Are we able to simplify that anymore? No, there's only one A under the radical, and 3 won't go into 1. So we're leaving the cubed root of A as the cubed root of A. Now here we are. We've got a 27. Is there anybody who knows if 27 is a perfect cube? Yeah. What number times itself 3 times gives me 27? 3. Okay, but that's not just a 3 that I'm pulling out. That's a negative 3. Now, you're like, Miss Johnson, you lost me. Okay, fine. Do 27. Do upside down division. 3 goes into 27 9 times. 3 goes into 9 3 times. So here I am. I have my set of 3. That set becomes 1 of that number. And I would pull out a negative 3 because the 27 was negative. So even if you don't know perfect cubes in your head, you can still do upside down division and get to the answer you should get to. Now, what do you notice about letter I? Okay, but what's under the radical? Fraction. So what's the first thing we got to do? Split them up, okay? But again, cubed root of 25c squared d to the third. I would agree there are a lot of numbers and letters and crazy stuff. But right now we're just focused on splitting it up. So the cubed root of 64 is your denominator. Now let's start with the 25. Is 25 a perfect cubed root? No. And is 25 going to have any sets of 3? You're like, I don't know. Okay, great. Then go up to the side and let's do upside down division. 5 goes into 25 5 times. Do you have a set of 3? No. So 25, the cubed root of 25 cannot be simplified. So go ahead and just put the cubed root of and put 25 back under the radical. Now, what about c to the 7th? Now again, it's all about the root and the exponent. Does 3 go into 7? How many times without going over? Twice. So c squared is outside the radical, but do you have any leftovers? Yeah. 2 times 3 is only 6, and there were 7 c's to start with. So how many are left over? There's 1 c left underneath. And what about d cubed? Do any d's come out? How many? 1 comes out, right? 3 goes into 3 one time, so 1d comes out. Now be very careful when there's a root other than 2, okay? You've got to make sure that the 3 is very obviously sitting on the ledge and is not the denominator of the d, okay? Is not the exponent of the d. So you want to be very, very careful. Now, the denominator, cube root of 64. Anybody know off the top of their head if that is a perfect cubed root? It is. Does anybody know what it is?
4 times
4. It is a 4. Very good. Again, you're like, Miss Johnson, I can't do it in my head. Okay, that's fine. Upside down division. 2 goes into 64 32 times. 2 goes into 32 16 times. 2 goes into 16 8 times. 2 goes into 8 4 times. And 2 goes into 4 2 times. I've got a set of 3 and I've got a set of 3. This set becomes a 2. This set becomes a 2. And everybody, what's 2 times 2? 4. So if you do not know off the top of your head, it's okay. Upside down division will help you find your answer. Now, we've moved into example 2. It still says simplify the expression, but we've got some different types of problems now. Look at the note that I've added underneath example 2. We simplify the radical if possible. So that's still upside down division. We're still looking at the radicals and deciding if we need to simplify them. Once we have simplified them, we add the coefficients of the terms with the same radical. So I want you to notice what they're asking us to do right here. When they say add the coefficients of the terms with the same radical, they are asking us to combine like terms. Now here's the difference in what you've learned before and what you're learning today. What you learned before said that like terms have the same variable raised to the same power. Today, like terms have the same radical part or the same radical piece. So let's look at what that means. First of all, look at letter A. We have 3 times the square root of 2 minus the square root of 6 plus 10 times the square root of 2. So first thing we're going to do is we're going to look at the radicals. Remember, terms are separated by plus and minus signs. So these are the terms when we talk about the terms. But let's look at them. Can the square root of 2 be simplified? No, because it's what kind of a number? It's a prime. Okay, so we cannot simplify the square root of 2. What about the square root of 6? Maybe, but what is, if you do upside down division, 2 goes into 6 how many times? Are there any pairs to come out? No. So we cannot simplify any of these radicals. So now our focus shifts to, are there any like terms? Are there any terms that have the same radical part? Okay, what are they? Okay, but give me the whole term. I need the whole like term. 3 times the square root of 2 and 10 times the square root of 2. Now, for those of you that are like, I don't get this, all right? Imagine if this was a 3x and a 10x. You wouldn't struggle, right? What would be the answer here?
13x.
13x. You'd add the coefficients and you'd leave the variable piece alone. Well, guess what? That's exactly what we're doing here. We're going to add the coefficients, leave the radical piece alone. So what is 3 times the square root of 2 plus 10 times the square root of 2?
13 squared.
13 times the square root of 2, and then we bring down what we have not used, which is the minus square root of 6. Now, can we combine anything else? Are there any other like terms?
No.
Then this is our final answer. Let's look at letter B. Will either of these radicals simplify? Because we got to do that first. Okay? Which one do you think might? 63. All right. 7 is a, what kind of number? Prime. So it's not going to reduce it. It's not going to simplify. But 63 just might. So let's go over to the side and let's do upside down division. What prime number goes into 63? 3. And it goes in there 21 times. What prime number goes into 21? How many times? 7. Now, that's a prime number, so we're done dividing. Here's my next question for you. Are we looking for pairs or sets of 3 this time? Why are we back to pairs? The root is square. It's a square root. Very good. So we've got a pair of 3s, and this pair of 3s becomes a 3. Now, here's another new situation. First of all, bring down the 4 times the square root of 7 because we've done nothing with it. This is the first time, though, if we bring down the minus 6, it's the first time that we've pulled something out from under the radical and there's already something sitting out there. So what do you think we're going to do with the 6 that's already out there and the 3 that we're pulling out? How are we going to combine them? Multiply them. Okay? Multiply them. So if we pull something out from under the radical and there's already a number out there, we're going to multiply. And what left over goes back under the radical? 7. Awesome. So we've got 4 times the square root of 7 minus 6 times 3, which is 18, times the square root of 7. Now we ask, can we combine like terms? Yes. These have the same radical part. So what's 4 times the square root of 7 minus 18 times the square root of 7?
Negative 14 times 7 squared.
It's not 7 squared. Make sure you know how to read it. It's the square root of 7.
Square root.
Okay, so it's negative 14. That was good work. Signs are different. Subtract and take the sign of the bigger number. Negative 14 times the square root of 7. Now, you'll notice a new set of directions above C and D. Not necessarily directions, but a note for you. All right, so let's look at that note because this is super, super important. You cannot multiply numbers and variables under the radical with numbers and variables that are outside the radical. So you cannot, let me say that again, you cannot multiply numbers and variables under a radical with numbers and variables that are outside the radical. So you got to make sure that if you're multiplying numbers together, they are either both outside of the radical or make sure they are both under the radical. Now, let's look at letter C, because if you look at letter C, everything kind of runs together. Let's look at this carefully and break this apart. Outside of the parentheses, you have the cubed root of negative 4. That is a monomial, okay? That is one term. what do you have inside the parentheses right here? Okay, does everybody see that and agree with that? There's a binomial, right? The cubed root of 2 minus the cubed root of 16. Now, there is nothing between this monomial and this parenthesis right here. So what operation are we supposed to implement? Multiplication. And do you see a property that you have learned and used all year long that we might need to do here? The distributive. So here's what I want you to do. Draw arrows. Even if you think, oh yeah, I got this, put arrows in your notes. So if you go back to study, you remember exactly what we did. Now here's the next question. Are all of the roots the same? Because we also can't multiply things if they have different roots. Do every single one of these radicals have the same root? Yeah, they all have a 3. You've got a 3, a 3, and a 3. So we're good. We can keep going. Now here's the next question. Can we multiply the negative 4 and the 2? Because the cubed root of negative 4 times the cubed root of 2 is our first step. Are we allowed to multiply the negative 4 and the 2? Are they both underneath the radical?
Yes, we can.
Then are we allowed to multiply them? Yes, we can. So this is the cubed root of what? What's negative 4 times 2? Negative 8. Awesome. Bring down the minus sign. Can we multiply negative 4 and 16?
Yes.
Because our next step is the cubed root of negative 4 times the cubed root of 16. Again, negative 4 and 16 are both underneath the radical, so we absolutely are allowed to multiply them. What is negative 4 times 16? Negative 64. Good. Now we've got to simplify. All right? Is 8 a perfect cubed root? Okay, I hear hesitation. So here, let's do it. 2 goes into 8 4 times. 2 goes into 4 2 times. We need pairs or sets of 3? We need a set of 3, and we have it. This set becomes a 2. But what comes out from under the radical? That wasn't a positive 8. That was a negative 8, which means a negative 2 comes out. Now, bring down your minus sign. Does anybody remember if 64 is a perfect cubed root? Yes, what was it? 4. Again, a 4 can't come out, though. What kind of 4 comes out? Negative 4. Now, what do you guys see right off the bat? Double negative, and they have to become positive. So what is negative 2 plus 4? Positive 2. Final answer is positive 2. And again, if you could not remember that 64 was a perfect cubed root, upside down division off to the side, and you will find it. Now, look at letter D. This is our last one for today, okay, but it's a big one. What do you notice about letter D? First of all, what is in the parentheses here? What type of polynomial?
Trinomial.
No. There's a binomial in those parentheses, okay? Also, that binomial is raised to the second power. So, this is a special product. Does anybody remember the name of this special product? You literally had this on your test yesterday, but do you remember the name of it? It is a binomial that has been squared. So, it is the square of a binomial. All right, put this in your notes, especially since no one could tell me. All right, put this in your notes. This is the square of a binomial, which means there is a shortcut, and you just used this shortcut yesterday. But let's put it off to the side. Okay, put it to the right of the problem. We are supposed to square the first term minus, what's that little formula we use to find the middle term? 2ab. And guys, I use the minus because there's a minus in the original problem. And then what's the last thing? I know the second sign is plus, and I'm supposed to do what? Square the b. So a squared minus 2ab plus b squared. That is the shortcut, and that's exactly what we're going to do right here. All right? What is the a of our problem? Give me the whole term.
2, 5, to the square root of 5.
2 times the square root of 5, and we're going to square it. Minus 2 times a. Again, what's our a?
2 to the 5.
2 times the square root of 5 times b. What's our b?
Negative 4.
All right, now be careful. Yes, technically negative 4, but I already brought the negative down. So if I've already brought the negative down, then it's just going to be a 4. Now you also have the option of making this a plus sign and bringing the negative down over there. But either way, how many negatives are in your problem up there? 1. So how many should be in your answer? Just 1. Okay, but I'll leave that up to you. I like to go ahead and bring the sign down, and that way I'm just dealing with a positive number. And then lastly, plus, what is my b again? 4. And actually, it's not 4, it's negative 4. All right, this is where we do have to be careful. All right, now let's do some math. And before you panic about 2 times the square root of 5 squared, just square each piece separately. What is 2 squared? 4. What is, now think about it, here it is visually, the square root of 5 times the square root of 5. What does that equal?
25.
The square root of 25, because I can multiply numbers that are under the radical. All right, minus, now let's go ahead and multiply. What are the numbers outside the radical here that we are allowed to multiply? Okay, there's a 2, a 4, is that it? There's another 2 right here, right? That's one big multiplication problem. So 2, 2, and 4. The only thing I'm not allowed to multiply is the 5 right here because it's underneath the radical. So guys, what's 2 times 2 times 4?
16, negative 16.
The negative's already there.
Oh.
So it's 16. And then what do you think I do with the square root of 5? Just bring it down. Remember, if that were an x, I'd just bring the x down and put it next to the 16. So the radical just gets brought down because I can't multiply it by anything. Plus, what is negative 4 squared? 16. Okay? Now, are we finished? No, because one of these radicals simplifies. Which of these radicals simplify? 25. And it's 4, the square root of 25 is what? 5. And what am I supposed to do with the 5 that comes out and the 4 that's already there? Multiply them. Then I bring down the negative 16 times the square root of 5 plus 16. All right, guys, what's 4 times 5? 20 minus 16 times the square root of 5 plus 16. Now I can box in my answer, right? No, because I have what? Like terms. I've got a 20 and I've got a 16. Now, I'll pull down the radical term first, just like I would pull down the variable term first. So negative 16 times the square root of 5. And then what's 20 plus 16?
36.
Plus 36. Now, can I combine that any further? No, they do not have the same radical piece. So this is my final answer. Now, I want to give you a jump start on tonight's lesson. All right, I want you to notice this step right here where you squared a radical, and I want you to notice what happened by the end. Okay, we took a radical times itself. When I multiply a radical by itself, my answer is the number under the radical. So I want you to write that in your notes, and this will be the last thing for now. Okay, when I multiply a radical times itself, the answer is the number under the radical. That means I can skip this step right here. I can skip, actually not the whole step, I could skip this step right here if I wanted to. If I understand that a radical times itself equals the number under the radical. And that will be key to what you watch in part 2. That is lesson 9.1, part 1.